Hello to all our food science professionals and industry enthusiasts tuning in from across the APAC region. Welcome to this explainer. Okay, let's dive into this. We are looking at a high-stakes battle happening right now on our supermarket shelves and in our processing plants. The enemy? Lipid oxidation. In our industry, managing this process is the absolute key to maximizing shelf life and protecting food quality. On-screen text, science, technology, and applications. Today, we are going to unpack the science, the technology, and the real-world applications of antioxidants in our food supply.
Here is our roadmap for today. Number 1, the threat of oxidation. Number 2, the free radical chain reaction. Number 3, nature's antioxidant defenses. Number 4, synthetic industry solutions. And finally, number 5, the power of synergy, which honestly is the ultimate industry secret to maximizing shelf life. You really won't want to miss that.
All right, let's start with Section 1, the threat of oxidation.
We all know lipids give food that essential structure and mouthfeel, but they have a fatal flaw. They are highly susceptible to oxidation. Did you know the rate at which an oil spoils is directly tied to its molecular structure? It is basically about how easily a hydrogen atom can be snatched away. Check this out. If a fatty acid with one double bond has a baseline oxidation rate of 1, adding just a second double bond makes it oxidize 50 times faster. And a polyunsaturated fat with 4 double bonds, it oxidizes a staggering 200 times faster. Literally, 200 times. This is exactly why those highly polyunsaturated oils are notoriously difficult to stabilize in production.
Moving right along to Section 2, the free radical chain reaction. Now, what's really interesting here is how this whole process acts like a destructive domino effect.
You see, oxidation isn't just a single event. It happens in 3 distinct phases. Step 1 is initiation. Atmospheric oxygen is usually pretty lazy, kinetically inert, but when trace metals or light get involved, they kick off the reaction, creating a highly reactive free radical. Then we hit Step 2, propagation. This peroxy radical reacts with a polyunsaturated fatty acid to create another free radical. It becomes this continuous, self-perpetuating loop. Finally, Step 3 is decomposition. This is where compounds break apart into the volatile molecules that completely destroy food quality. You can see the actual chemistry taking place right here. Notice how atmospheric oxygen enters the cycle during the single electron oxidation of a polyunsaturated lipid. It forms those peroxy radicals that just keep driving the reaction forward. Take a moment to absorb this molecular transformation. This continuous loop, it is the ultimate enemy of shelf life. So this brings us to a really fascinating question. If hydroperoxides, which are formed during propagation, are inherently odorless, and they are, why does oxidized cooking oil smell so horribly rancid? Well, the answer is in the decomposition phase. Reduced metals catalyze the cleavage of those hydroperoxides, breaking them down into short-chain aldehydes, ketones, and alcohols. These volatile breakdown products have incredibly low flavor thresholds. They are the actual culprits your nose detects as rancidity. Okay, Section 3, nature's antioxidant defenses.
Living organisms possess highly sophisticated ways to protect their cellular membranes. And in the food industry, we use these natural defenses as crucial circuit breakers. Because, the best way to stop a chain reaction is to prevent it from ever starting. That is the job of metal chelators. Think of a simple polyacid chelator like EDTA as a pair of chemical handcuffs. They lock up reactive trace metals by fully occupying their liganding orbitals. Kept securely bound, these metals absolutely cannot initiate a free radical riot.
But what happens if the reaction has already started? Enter nature's premier chain-breaking antioxidant, alpha-tocopherol. You probably know it as vitamin E. It is incredibly efficient. Alpha-tocopherol readily donates an electron to reduce peroxy radicals into hydroperoxides. By doing this, it puts a kinetic hindrance on the propagation chain reaction. It basically sacrifices itself to protect the vulnerable polyunsaturated lipids. Now, in food processing, we often have to choose our defensive strategy. Natural antioxidants, like tocopherols or rosemary extract, are brilliant biologically. Plus, they easily meet consumer demand for clean labels. But they are fragile, and they often degrade during processing. Synthetic antioxidants, on the other hand, are engineered specifically to survive high-heat environments, like commercial baking and deep frying. They provide what we in the industry call carry-through protection. Let's move to Section 4, synthetic industry solutions, and see how this builds our optimization strategy. To ensure foods remain stable during complex manufacturing and long supply chains, we rely on the commercial heavy hitters. Two of the most common synthetic options are BHA and BHT. Notice that both are hindered phenols. The tertiary butyl groups surrounding the hydroxyl group actually suppress antioxidant activity through steric hindrance. That makes them less effective in some vegetable oils, but it allows them to survive the intense heat of baking. And what is truly fascinating is how they work together. Essentially, BHT brilliantly replenishes hydrogen back to BHA, regenerating its effectiveness. Next up is TBHQ, or tertiary butyl hydroquinone. For those of you working with highly polyunsaturated frying oils, TBHQ is your ultimate protector. It has moderate fat solubility, slight water solubility, and importantly, it does not cause discoloration when it interacts with metals like iron. It is widely considered the absolute best antioxidant for protecting oils under the punishing stress of deep frying.
Then we have propyl gallate. This antioxidant is fantastic for meat products like rendered fats and pork sausages. However, it does have specific limitations. Its low melting point makes it pretty much ineffective for high-heat frying. Furthermore, its slight water solubility makes it prone to complexing with iron salts. Unfortunately, that can lead to a really unappealing dark discoloration in certain food applications.
Which brings us to Section 5, the power of synergy. So the crucial point is,
Commercial stability is rarely achieved with just one single compound. The real magic in food science happens when we combine forces. We use synergistic add-ins to create a 1 + 1 = 3 preservation effect. Citric acid and ascorbic acid act as natural metal chelators, handcuffing those reactive metals. Ascorbic acid also regenerates primary phenolic antioxidants. Lecithin provides metal chelation properties, while compounds like 3,3-thiodeopropionic acid act as powerful synergists when combined with primary antioxidants like BHA. By blending a primary chain-breaking antioxidant with a synergistic chelator, we attack oxidation from multiple angles simultaneously.
As consumer preferences shift and processing technologies advance, the science of preservation is constantly evolving. So, how will the balance of natural versus synthetic antioxidants shape the future of clean-label food processing right here in the APAC region? It is a complex challenge, balancing shelf life, safety, and consumer demand. I will leave you with that thought. Thank you so much for joining me for this explainer, and keep innovating.